Hi, this is the final presentation of Team 4. I'm Jian Lee. First, I will briefly introduce the paper and related works for improvement. Then Myung-Hwa will explain and analyze the approach that introduced new self-supervised tasks. Lastly, Jong-min will introduce the approach in terms of data augmentation and make a conclusion of our project. The topic targeted in this paper is that a policy trained in one environment might not generalize with other new environments. Even if a policy is trained well, it can fail the test if the environment changes. So this paper proposed a method for adapting a policy in a new environment that does not provide a level signal. The proposed method is called PAD, which stands for Policy Adaptation During Deployment. It learns a policy in a single training environment and deploys the policy in a target test environment. And then it adapts the policy during deployment itself. PAD only uses the data collected during deployment and adapt online using a self-supervised training signal. This can be done by introducing self-supervision to obtain free training signal during deployment. The PAD algorithm consists of training phase and the adaptation phase. In training phase, there are signals from both the reward and self-supervised task. So policy is jointly trained by optimizing the RL and self-supervised objectives. However, in the adaptation phase, only the self-supervised objective remain active. So observations are collected from the test environment and adapt policy with optimizing only the self-supervised objective during deployment. In this paper, two different self-supervised tasks are considered. First one is the inverse dynamic model. It takes the state before and after transition and predicts the action in between. So it is useful for tasks that require motor control. And the other one, a rotation prediction task. An observation is rotated by one of 4 different angles and casts this as a 4-way classification. So it is more suitable for tasks that require scene understanding, such as navigation tasks. In network architecture, it consists of a feature extractor phi-E, self-supervised head phi-S as a model, and RL head phi-A as a controller. The goal of PAD is to update phi-E at test time using gradient from a self-supervised task, so that phi-E can generalize. In the paper, random crop was used as data augmentation, and inverse dynamic model and rotation prediction were used as a self-supervised task. We focused on the self-supervised task and data augmentation to improve PAD. Our related works of improvement approach like as follows. The details will be explained when introducing each approach. We considered these 4 models as our baseline, referring to the experimental result of the paper. We evaluated baseline and our improved model on both conditions with and without PAD. To evaluate the generalization performance, we focused on the following 2 test environments, random colors and video background.
We replicated the PAD by referring to the original paper's code and got experimental results with the hyperparameters used in the paper. Similar to the paper, our replication results show that the self-supervised task idea was better than the rotation prediction task. Besides, in most cases, the PAD models showed better performance. Based on these replication results, we selected 4 tasks of 4 domains and decided to focus on these tasks in order to experiment our approaches within a given time. We chose relatively difficult tasks with low rewards. For improvement, we implemented and evaluated these 3 approaches. The first approach is to modify the rotation task used in our base paper. In the paper, rotation-based models show relatively low performance. We thought the reason for this is that the task is too easy to have better feature running for dynamic continuous motions. So we modified the task and network architecture to predict 360 rotations. In order to serve the size unbalance of rotated images, we cropped and used the central image in which all rotated images are overlapped. In addition, for better feature running, we changed the problem. In the classification, 2 different rotated images are recognized as just different ones rotated by different angles. On the other hand, a regression model can recognize on different angle difference between the two. So we thought that a regression model would be more suitable for our rotation task. We implemented our model using mean square error as loss function and applied it to PAD. The second approach is to introduce MCAL as a self-supervised task of PAD. This task introduces an auxiliary transformer module to CAL, which is a representative method of constructive learning. MCAL captures the relevance among consecutive inputs and reconstructs masked representations by using this transformer module. And MCAL uses momentum constructive learning to optimize encoder and transformer. It used the constructive rules to jointly optimize CNL encoder and transformer, while the reconstructed features should be similar to the ground truth ones. Using these features, we applied MCAL to PAD in a way that adopts policies using constructive rules in test environment. These are the evaluation results in random color test environment. As you can see, the results for our baseline show that the adapting of PAD is effective. In the case of the first approach, the models achieved the best performance on cheetah run task, but PAD didn't improve the performance. For the second approach, it can be seen that the models received a lot of help from PAD in the worker work and cheetah run task. Next is the result in video background test environment. Our first approach shows good performance for worker work task. However, in most tasks, our approaches didn't outperform baselines. Our new rotation task is more difficult than original task, but the number of features is smaller due to the cropping central images. And for our second approach, MCAL samples a set of consecutive transitions from the replay buffer and apply it as a sequence. Therefore, it seems that sufficient episodes are needed to ensure that the self-supervised learning is properly performed by PAD. When we increase the number of episodes, PAD models for our method actually showed better performance. In addition, both approaches seem to require more experiments, including hyperparameter tuning. Each approach took 1 to 2 weeks to pre-train, so we haven't been able to experiment sufficiently due to the time and resource limitations.
As the third approach, we applied data augmentations other than the existing random crop within the self-supervised learning task as IDM enrolled. Among various augmentations, we selected some of them by referring to the red paper that showed good performance by applying random augmentations to the original image, because we thought that other augmentations might be adapted better in PAD. We chose one with the best performance in each of a single augmentation and the combination of two augmentations, referring to the paper. So rotation and the combination of grayscale and random crop were selected. Since using only rotation showed better performance than the combination in our experiments, we additionally applied the combinations of random crop and rotation to our method. These are the results for them in 2DM control tasks. As you can see, there was no improvement in performance when augmentations other than random crop were applied. So we applied another additional augmentation, a random that was used in DARE2 paper. DARE2 was a paper that was initially found when surveying papers for introducing self-supervised learning tasks. It uses random shifts to augment input observations as well as regularizing the Q function learned by critic. However, since it does not have additional loss, we thought that it is not meaningful to apply PAD. So we decided to use only the augmentation technique in DARE2. Here, the original images of size 84 by 84 are padded each side by 4 pixels and then randomly cropped back to the original size. We applied this to our PAD method and we could obtain the following results in random color environments. In the results, our method showed the highest performance except for finger turn each task. In addition, as the author argues, IDM mostly performed better than ROT or at least had similar performance in our method. The results in the video environment were similar. Our method showed the highest performance except for the finger task, and the IDM with PAD was always the best. These results show that applying DARE2 random shift as augmentation improves performance when using IDM as a self-supervised learning task and the performance of PAD compared to the existing method. The following is an additional analysis of why a random crop is better only in finger turn each task. This task makes the tip of the free body to overlap with the target. In random crop, as the size of the target is enlarged by performing crop, the difficulty of the task becomes relatively easy. This can be the reason that it shows better performance than random shift, which does not change the size of the target. Our simulation results are as follows. As you can see in the videos, the generalization is performed well even in completely different environments from training. In conclusion, we could once again confirm that applying PAD is a good way to solve the generalization issue. Generalization is more important because it is also a major issue in applying the model learned in the simulation environment to the real. In addition, we found that using PAD may lead to large performance improvements in terms of generalization depending on the characteristics of self-supervised learning tasks as in M-curve. We introduced the new tasks as an approach for improvement, but they showed the improvements only for some PM control tasks. We had a time limit for this approach because we could not perform many experiments, including hyperparameter tuning, even if PAD was sensitive with respect to the self-supervised learning task. On the other hand, applying the augmentation of DRQ showed overall improvements except for the finger turn each task, where the random crop is more useful due to the characteristics of the task. When comparing the results of IDM with PAD, our method showed performance improvements of up to 186% in random colors and up to 120% in video backgrounds. Through our experiments, we have confirmed that the choice of self-supervised learning tasks and augmentation is important in using PAD. Therefore, we think it would be good to conduct research that automatically selects learning tasks and augmentation that are more suitable for a given new environment as future work. These are our references. Thank you for listening.